Unit 1, Lesson 10, 1.31, Dynamics. We covered kinematics, now let's review dynamics from grade 11. Physics is the study of motion and interactions. Equipped with the tools of vector kinematics, we may now inquire deeper into the concepts of motion by investigating the causes of motion. This branch of physics is called dynamics. As a brief history, ancient civilizations were aware of the motions of the planets and the stars. Many of them realized a heliocentric, sun-centered model of our solar system. Amongst lovers of wisdom, i.e. philosophers, there were those who proposed that Earth is at the center of the universe and that all objects revolved around us. In Europe, there were great debates about this geocentric model versus the heliocentric model of our solar system. Most of the debaters based their beliefs or based their proposals on beliefs rather than actual empirical evidence. In the late 1500s, Tycho Brahe, a nobleman astronomer, proposed an idea that essentially became the bedrock of all modern science. His idea was this: in order to settle this debate between the geocentric and the heliocentric, let us make careful observations, precisely record data, then construct a logical and reasonable proposition about the observations. Analyzing models based on empirical data to arrive at meaningful evidence-based theories is the true scientific endeavor. So Tycho Brahe wanted to settle the debate by saying, let's just look at the thing and analyze the data and see who's right. Now, using optical instruments, Tycho Brahe meticulously observed planetary motion and recorded data over many, many years. Unfortunately, he died before completing the mathematical investigations of his own data and never saw how his ideas changed the course of civilization. Fortunately, however, Tycho had hired Johannes Kepler, a brilliant mathematician who brought Tycho's observational data to fruition with a tremendous feat of mathematical ingenuity. Kepler tried to fit circular orbits to Tycho's data, but failed for Mars's orbit. In other words, Mars's orbit was not circular. Now you may ask, why did he want to fit circular orbits? Well, because it was believed that the heavens, which was the cosmos at the time, was perfect in every single way, and no shape is more perfect than a sphere, so all the planets and the stars and the moons were believed to be spherical, and all the orbits were assumed to be circular, because that would be a perfect shape. And so based on that, Kepler had tried to use Tycho Brahe's data and see if the orbits were indeed circular. Most of them were good approximations to circles, except Mars. Mars's orbit was not circular, it was off-circular. And Kepler really trusted Brahe's data. The discrepancy was so large that Kepler realized the orbits could not be circular. So having trust in Brahe's data, Kepler said, well, this discrepancy of Mars's orbit is too much for this to just be a human error. It must be the case that the orbits are not circular. So courageously, he abandoned circular orbits and instead tried to fit elliptical orbits to Tycho's data. And much to his surprise, it matched the data and supported the heliocentric model. Now, I remind you what an ellipse is. An ellipse is kind of like a squished circle, kind of like an egg shape almost, but more symmetric than an egg. And it's very, very close to being circular. In fact, most of the planets go very nearly circular orbits, but some planets have more elongated orbits and thus are elliptical more than circular. Now, having done all these observations, Kepler concluded these following planetary laws. There's 3 Kepler's laws of planetary motion. 1, all planets move in elliptical orbits, not circular orbits, with the sun at one focus. So an ellipse is this elongated kind of circle, and in a circular case, we have one special point, which is called the radius, and everything else is the same distance from the radius. In an ellipse, you have 2 of these centers. We don't call them centers with ellipses, we call them focus points or foci. And so Kepler said, if I use Brahe's data, I'll notice that the planets go in elliptical orbits with the sun being at one of these focal points, these foci. That was his first law. Then he said, if you take a particular planet, suppose we take Saturn, and we observe Saturn at one point in its orbit, and let's say we wait a month and we observe Saturn again in a different position of its orbit. Now, Kepler was a brilliant mathematician. He was able to deduce the area covered in this planar motion as Saturn went for about a month, let's say, around its orbit. Now, later on in Saturn's orbit, as it gets closer and closer to the sun, Kepler observed the position of Saturn again and waited again another month, 1 month, exactly the same period as before, and calculated or observed the position again from Brahe's data, and again calculated the area in that month. And much to his surprise, he learned that if the time intervals are the same, so a month, a day, a week, doesn't matter. If the time intervals are the same, then the area swept will also be the same. Okay. This was true for all the planets. So when a scientist like Kepler sees this pattern, he doesn't think it's coincidence. It can't be this coincidental. There must be a pattern. There must be a reason why this is the case. Now, it was not known to Kepler what this reason was. Later, many centuries later, I guess, we discovered that this is a particular law of nature. It is called the law of conservation of angular momentum, which is something you'll learn in post-secondary. His third law was very surprising as well. He said that for all the planets, this particular relationship is true. T, remember, was the period, was the seconds, was a time from one point to another in the orbit. If you take any time and you square that time, he realized from his calculations that that will be proportional to the cube of what we call the semi-major axes. So an ellipse has two axes, the semi-minor axes, the shorter of the two axes, and the semi-major axes. So if you take this semi-major axis and you put a dot in the middle, then this length is called A, the semi-major axis, and if you cube that amount for the planet's orbit, it will be the period of the revolution of the planet. So it's a very, very remarkable relationship. I think I misspoke just earlier. T would have to be the actual orbital period. So for example, the Earth, the orbital period is 365 days. You convert that to seconds. I think it's 86,400 or 84,600 seconds, whatever it is. If you square that amount, that will be equal to the semi-major axis of the Earth, let's say. So it's a very remarkable law, and believe it or not, this is the particular law that Newton used to figure out his universal law of gravitation, which is what we'll learn later on in our gravity unit. So Kepler was able to use Tycho Brahe's data and come up with 3 laws of planetary motion. What's interesting is that Kepler had no idea why these laws were true. He just found them using data, but that was good enough for the time. It was a very remarkable step because not only did it show that we can take data and analyze it and come up with mathematical arguments to come up with physical laws, but it also settled the argument. We do live in a heliocentric solar system, with the sun being at the focus of the elliptical orbits of every planet. And there are special relationships between all the planets in his second law and his third law. So this is a very, very remarkable point in human civilization when a very deep argument that has been raging on for centuries and millennia is finally settled just by looking at the thing and analyzing the data. During the same period, Galileo was also investigating motion by rolling balls down inclined planes and by swinging pendulums. He was able to conclude a very remarkable result, which we will call the principle of inertia. which states, as you know from grade 11 by Newton's laws, all objects remain at rest or move with constant velocity unless disrupted by an external influence. So during this time, we're dealing with Galileo's discoveries and Brahe's data and Kepler's formulation. Remarkably, Galileo also built his own telescope and was the first person to point his telescope at the moon and notice that the moon is full of craters. So unlike the belief system that all heavenly objects are perfectly spherical, unblemished, Galileo saw with his own eyes, using his own built telescope, that the moon is full of craters, so it is very much not perfect. It's full of blemishes, and therefore another belief was thrown out the window, that everything in the heavens was perfect. He also was the first person to point his telescope at Jupiter, the largest planet in our solar system, and notice something remarkable. So if we say this is Jupiter, he noticed 4 dots. From night to night, these 4 dots change positions, okay? And concluded that the only way that these 4 dots can night after night change positions would be that they can't be stars. Stars would be too far away to change that much in that little amount of time. So he concluded that these must be Jupiter's moons that are orbiting Jupiter. And sure enough, they were. And that's important for us because it also shows that not only is the Earth not at the center of our solar system, that there are objects in our solar system that orbit other objects. So the moons of Jupiter orbit Jupiter. They don't orbit the sun or the Earth. So we get this idea again that the Earth is not special at all. We have a moon, that's good, that's fine, but doesn't make us special in the solar system. We are not at the center of the solar system, and there are moons that orbit other planets. Of course, later on, there were discoveries about Saturn and other types of moons around other planets as well. So really, this observation of Jupiter was monumental in showing, yet again, that the Earth is not special at all when it comes to its movement in the solar system. So after all this, after Kepler's deduction of the 3 laws of planetary motion, after Galileo's discoveries of Jupiter's moons and the principle of inertia, and the works of Descartes and Huygens, Newton came along and tried to build a set of laws, or state a set of laws, that can essentially explain all of Kepler's laws and the observations made by Galileo and the work done prior to Newton by Descartes and Huygens. And he did. During the plague of 1664, he went home for a couple of years and wrote down 3 laws of motion. He also deduced a model for universal gravitation. He worked on his theory of light and colors. And in doing his laws of motion and the universal gravitation, he had to use a new tool which he invented himself, which we call calculus now. So in order to come up with these laws and apply them to different spherical objects in the cosmos, he had to invent calculus. He did all this before he turned 23, which is remarkable, and which is one of the reasons why he's regarded as one of the greatest scientists, if not the greatest scientist in history. So in 1664, he works on this and essentially finishes his work by 1666, and he puts all his work aside. He doesn't publish, he doesn't really tell anyone, and it wasn't until about 20 years after he finished, or he had done his preliminary work, that Edmund Halley encouraged him to actually put all his works together in a single volume, which is called the Mathematical Principles of Natural Philosophy. So Newton in the Principia, which is usually the shortened version of the name, in his Principia wrote the laws of motion, the universal gravitation, using calculus in a monumental work in 1687, and that changed the course of history. That is essentially how our society evolved into building mechanisms, machines, all sorts of things, structures, buildings, bridges, all abide by Newton's laws of motion. So Newton was a gift to the human race. The intellectual inheritance that Newton gave us propelled our civilization into what we know now. It's hard to say where we would be without the 1687 publication. We would be far, far behind where we are now, because it takes hundreds of years for these ideas to be developed. And it's truly a masterpiece, and it's no doubt that on a statue at Trinity College, it says in Latin that he surpassed the human race in intellect. So a very remarkable feat of mathematical ingenuity to explain all these people's works in one volume was a remarkable feat by any scientist. And Newton later went on to write a book on optics and light as well. 1.33, Motion Fundamentals. Dynamics is the study of what causes motion. We have worked with the concept of distance, time, speed, and acceleration. But now, let us look at these concepts more deeply and connect them with a model of what could cause these quantities to change. Motion is the relation between space and time. That's why distance equals space times time. So here we have distance, here we have time. This is the connection, speed, motion. By including the direction of motion, we can say that velocity is the difference between an object's final and initial position divided by the time that passed from the start to the end of the motion. So that's just v is equal to delta d over delta t. Recall that graphs reveal important relationships between quantities, and they play a crucial role in our understanding. So consider three different motions, figure 1a, 1b, and 1c. Here is a motion that is stationary because the displacement isn't changing. Here's a motion in which the displacement is changing uniformly. The slope of this graph gives us vt. The slope of a diagonal line is straight. So if we were to convert these graphs into their associated velocity time graphs, we would get these graphs here. So no velocity, constant velocity, uniform increasing velocity, so constant acceleration. Now, the reason I'm telling you this is because I want to tell you that Newton's laws of motion, which you're very familiar with, which we'll reintroduce in a moment, work for particular situations. When you have observers or motions that are moving relative to each other uniformly, then Newton's laws apply. In other words, if you have an object A that is at rest, and you have an object B that is moving with a constant velocity, then Newton's laws tell us how to relate these two references. These reference frames, in this case, if you're in reference frame for A, you're not moving, you're watching B move away from you at a constant velocity. If you're in reference B, if you're on the moving object, what you could say is that actually it's not me that's moving. B, if you're on B already, you're not moving at all. It's actually A that's moving in the opposite direction. So you can either be in reference A, where B is moving to the right at constant velocity, or you can be at reference B and have A go left at constant velocity. These are indistinguishable. You cannot distinguish between either of these. You cannot say definitely that B is moving, because you can jump on B's car, let's say, or attach yourself to the reference point of B and say, it's not me that's moving, it's the other person in front of me that's moving in the opposite direction. So physics cannot be built on the different views of different people stating different results. It must be consistent for everyone. Therefore, Newton's laws work just as well in this case as they do in this case. In other words, graphically speaking, what you can say is, if I'm this object not moving, I should conclude the same physics as this object moving at constant velocity. How can I justify that? Well, if you notice, these two are horizontal lines. So if I were this object and I attach myself to this object, then relative to this object, I'm no longer moving. In other words, I can redraw this graph and say, actually, I'm not moving at all. It's this other object that is moving in the opposite direction. So just by attaching yourself to a moving reference frame moving at constant velocity, you can arrive at the same exact results. All to say that reference frames that move at constant velocity relative to each other conclude the same exact physics. And in that realm, we are able to apply Newton's laws without any problems. Now, as you learn physics going forward, you may ask yourself, well, what if reference frames are not moving at constant velocity to each other? What if a reference frame is moving at a constant velocity and another one is moving at an accelerated rate? How do I conclude the same physics? In other words, you can be standing and you can drop an object and you can say, I wonder what the world looks like as the dropped object. Well, the dropped object is under the influence of gravity, so it's accelerating. And unfortunately, Newton's laws are not very well suited to deal with accelerated reference frames. In other words, it's difficult to relate these two graphs to this graph because this graph is accelerating. But we are able to analyze these. We just need to know a little bit more physics. And when you do learn Einstein's theory of general relativity in university, if you take physics, you'll realize how to relate constant velocity motions to accelerated motions. In this course, we will learn the special theory of relativity at the end of the course. That's our last unit, but we will not deal with general relativity. But those of you who are curious how to know the feeling of being dropped and knowing what the world would resemble will need to learn general relativity. Now, we will deal with accelerated reference frames in this course when we do circular motion, but I'll tell you what the deficiencies are in Newton's laws when we're dealing with that. So this argument was just to tell you that Newton's laws of motion work very well in what we call inertial reference frames that move with constant velocity relative to each other. But they don't work so well. We have to add a few things when we're dealing with accelerated reference frames, which we'll see some examples in circular motion. Continuing onwards, physics is not only about just answering questions, it's also being able to ask proper questions. So I've given you 4 little points here on what to ask yourself when you're reading a question in dynamics. So when you're reading a question, ask yourself, what objects are undergoing the motion? What is causing the motion? What is qualitatively significant about the motion? And what is quantitatively significant about the motion? So these 4 things should be in your mind as you're reading a dynamics question or any kind of physics question in this course. So for instance, this is a terribly worded question. A town is 100 kilometers and 1 hour away. What is the speed? Well, what is undergoing motion? We don't know. What is causing the motion? We don't know. And it's not even well posed. What is the speed of what? What is the thing that's undergoing motion? A better question could be, a town is 100 kilometers away from a person's home, and if the person takes 1 hour to drive to town, what was their average speed? So now we see that it's a person in their car that is undergoing motion. The thing that is causing the motion could be stated as the car's engine. What is qualitatively significant could be that the motion was uniform, and what is quantitatively significant about the motion could be the calculation of the average speed. So average speed, total distance over total time, 100 kilometers in 1 hour gives you an average speed of 100 kilometers per hour. So having a proper question and having these 4 points in your mind, you're able to arrive at a meaningful answer. And when you're reading these types of questions, you should have these types of questions to ask yourself so you have a better understanding of the physics involved. Now, one other thing before we finish this section. In kinematics, we did not deal with the mass of an object. So when you were doing projectile motion in grade 11, you didn't ask the mass of the projectile. You calculated the trajectory in different kinematical quantities. But then you learned dynamics in Physics 11 and realized that mass is a crucial part of motion. And so you had to incorporate mass in Newton's laws because heavier objects are harder to push than lighter objects. And so the mass of an object plays a key role. And so in this particular course, Physics 12, we will deal with mass much, much more often than we did with grade 11 because it's a very, very important quantity in motion.